In this fourth class of our automotive air conditioning course, we're going to focus on the system's compressor. In this lesson, we will go deeper into its importance, its internal operation, and the different variations that exist depending on the type of vehicle and its technology. The compressor is considered the heart of the air conditioning system, since it is responsible for drawing in the refrigerant in its gaseous state and compressing it so it can continue its cycle within the system. For this reason, understanding each type and how it operates will allow you to diagnose failures with greater precision and correctly select the appropriate compressor for every automotive application. To begin, it is important to understand that the types of compressors used in automotive air conditioning are basically 7. This classification is based on their mechanical design, the way they perform compression, and the type of control they use to adapt their capacity to the vehicle's thermal demand. Although they all perform the main function of compressing the refrigerant, their characteristics, efficiency, durability, and the way they interact with the vehicle's control system can vary significantly. This is why knowing each one of them is essential for any automotive air conditioning technician. 1. Fixed-stroke automotive compressor with clutch. This is a compressor with several pistons driven by a rotating plate that is fixed axially, generating a fixed stroke in the pistons. It is mainly used in medium to high-power vehicles. Since the piston stroke or displacement is always the same, the amount of refrigerant drawn in by the piston is constant for each revolution of the compressor. Therefore, when less refrigerant is required, because the desired temperature has already been reached, the only option is to disconnect the compressor from the system by disabling the clutch current to avoid excessive cooling. Due to this limitation, this type of compressor cannot adapt to the thermal load required by the vehicle. For this reason, the system turns the compressor on and off by activating and deactivating the clutch to regulate the cabin temperature. Although it is a simple and robust system, its energy efficiency is lower compared to variable displacement cooling capacity compressors. 2. Variable stroke piston compressor with clutch and mechanical control valve. Just like the fixed-stroke compressor, this is a multi-piston compressor driven by a plate, but the difference is that this plate can move axially inside the compressor to generate a variable piston stroke. If the piston stroke is variable, when less cooling is needed, the stroke can be shortened to draw in less refrigerant gas. This allows reducing cooling production instead of shutting the compressor off directly. To achieve variable piston stroke, this compressor uses a mechanical valve that, depending on the compressor's suction pressure, manipulates part of the refrigerant flow to push or pull the wobble plate axially. For example, when suction pressure is slightly lower than normal, the stroke control valve shortens the piston stroke, since low pressure is a sign of lack of heat or excess cooling. On the other hand, when the compressor's suction pressure is higher than normal, the stroke control valve increases the piston stroke to draw in more refrigerant gas. Remember that a higher than normal suction pressure indicates excess heat. This type of compressor is mostly used in medium to low power vehicles. Thanks to its design, it can modify its capacity depending on cooling demand, resulting in reduced clutch wear, better fuel economy, and more stable system operation. This type of compressor offers superior performance compared to fixed-stroke compressors. 3. Variable stroke piston compressor without clutch and electronic valve. This is a multi-piston compressor driven by a plate that can move axially inside the compressor to generate a variable piston stroke, but in this case, the axial movement is controlled electronically. This type of compressor uses an electronic valve or solenoid whose function is to allow or block refrigerant flow into the compressor. The AC electronic control unit manages this valve based on readings from pressure and temperature sensors. The electronic valve also controls the piston stroke length, regulating cooling capacity. For this reason, it does not need a clutch. If the valve blocks refrigerant flow, the compressor simply does not compress. This allows the compressor to remain permanently coupled to the engine, but operating only when the system requires it, reducing vibrations, improving performance, and extending the lifespan of the assembly, in addition to offering more precise thermal comfort control. Remember that in the description of this video, you will find the link to the test for this class and more information on this topic. There you will find additional material, practical evaluations, and downloadable resources that complement what you've learned, helping you to strengthen your knowledge and gain a deeper understanding of how these compressors work. 4. Automotive vane compressor with clutch. In this type of compressor, the gas volume is progressively reduced by the movement of the vanes. It stands out for its high efficiency and low noise level, making it attractive for smaller vehicles. However, many technicians consider vane compressors to have lower durability than piston compressors commonly used in the automotive sector. Although they operate smoothly and steadily, the nature of their design causes the vanes to be in constant friction against the housing, increasing internal wear and reducing their lifespan compared to more robust types. 5. Automotive scroll compressor with clutch. In this compressor, the gas volume is reduced through orbital displacement. It consists of two spiral-shaped rotors, one fixed to the housing and another mobile, driven by the vehicle's engine. They're mounted with 180 degrees offset, producing smooth and continuous compression. This type of compressor is highly efficient, quiet, and produces fewer pressure pulsations, improving comfort inside the vehicle. Additionally, because it does not use pistons, it has fewer moving parts, reducing the chances of mechanical failures. Remember that in the description of this video, you will find the link to the test for this class and more information on this topic. There you will find additional material, practical evaluations, and downloadable resources that complement what you've learned, helping you to strengthen your knowledge and gain a deeper understanding of how these compressors work. 6. Hybrid automotive scroll compressor. Hybrid vehicles are powered both by the gasoline engine and the electric motor. Since the combustion engine is not always running, an alternate method is needed to compress the refrigerant. The hybrid compressor is essentially composed of two scroll-type compressors. The front half operates as a traditional mechanical compressor driven by the accessory belt. The back half operates with a three-phase 144-volt AC motor. The vehicle HVAC system determines the cooling demand and sends the signal to the compressor controller. The controller takes the 144 volts DC from the hybrid battery, converts it to 144 volts AC, and generates the required speed to produce the appropriate refrigerant pressure. This design allows the air conditioning system to operate under any condition, even when the combustion engine is off, which is essential in modern hybrid vehicles. 7. Electric automotive scroll compressor. This compressor uses an electric motor independent from the vehicle's engine. The motor is brushless, with a permanent magnet rotor and a wound stator. It requires an inverter that converts the battery's direct current into alternating current. The AC controller sends speed signals to the inverter, thereby regulating the compressor speed. Since oil could reduce cooling performance, an oil separator is used to improve efficiency and allow clean operation of the electric motor. The electric motor operates at high voltage, generally 200 volts or more, which is why a highly insulating oil is required to prevent short circuits. Additionally, electric compressors are quieter, providing greater comfort. Speed control saves energy and improves hybrid or electric vehicle range. The system can keep the AC running even when the vehicle's engine is idling or turned off. Regarding maintenance, it is essential to use the proper high insulating oil. If dye is used for leak detection, it must be an SAE-approved dye. An incorrect dye could affect the oil's insulating properties and damage the electric motor. Finally, since electric compressors are hermetically sealed, they do not have a shaft seal, and there is no risk of direct refrigerant leakage to the outside.